December 1939, Warsaw, Poland. A wooden crate marked with German military insignia sat in the back of a British intelligence truck, rattling over cobblestones as it made its way through the darkness toward the Polish border. Inside that crate, wrapped in oilcloth and packed with straw, was a machine that would change the course of World War II. Not a weapon, not a vehicle. A typewriter-sized encryption device called Enigma, smuggled out of Poland just weeks before the Nazi invasion crushed all resistance. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Captain Elizabeth Hartley of British military intelligence stood in the cargo bay, her hand resting on the crate as if to reassure herself it was real. She had spent 3 years studying cryptography at Cambridge, another 2 working in the Signals Intelligence Division, and she thought she understood the mathematics of secret codes. But nothing in her training had prepared her for what the Polish intelligence officers had just handed over to Britain. They called it impossible to break. The Germans believed their communications were absolutely secure, and the Poles, after 7 years of secret work, had proven everyone wrong. The truck crossed into Romania just before dawn. Hartley barely slept during the journey, her mind racing through everything the Polish cryptographers had told her in their hurried briefing. They had been breaking German Enigma codes since 1932. 7 years of intercepted messages, 7 years of reading Hitler's most secret military communications. And now, with Poland about to fall, they were giving everything to the British. The machine, the methods, the mathematical breakthroughs that made it all possible. At a safe house in Bucharest, Hartley finally opened the crate under proper lighting. The Enigma machine looked deceptively simple. A keyboard like a typewriter, 3 rotors that could be arranged in different positions, a plug board with cables that could be connected in millions of combinations. Press a key, and a lamp would light up showing the encrypted letter. The person receiving the message would set their Enigma to the same starting position, type in the encrypted text, and the lamps would spell out the original message. Perfect security, the Germans believed, because the number of possible settings exceeded the number of atoms in the universe. Hartley photographed every component from multiple angles. She measured dimensions with precision instruments. She documented the wiring inside each rotor, tracing how electrical current flowed through 26 contacts in a specific pattern. Each rotor was different. Each one scrambled the alphabet in its own unique way. And after each key press, the rotors advanced like an odometer, changing the encryption with every single letter. The Germans had built mathematical complexity into a portable machine that any radio operator could use in the field. The technical specifications seemed impossible at first glance. 3 rotors, selected from a set of 5, arranged in any order, gave 60 possible rotor configurations. Each rotor had 26 starting positions, multiplying the combinations into the millions. The plug board could swap 10 pairs of letters, adding trillions more possibilities. And the rotors advanced at different rates, the rightmost rotor stepping with each key press, the middle rotor stepping every 26 letters, the left rotor stepping every 676 letters. The encryption changed constantly, never repeating the same pattern twice within practical message lengths. British cryptographers had been trying to break Enigma since 1926, when they first learned of its existence. 13 years of failure. 13 years of intercepted German messages that looked like random gibberish, impossible to decode without knowing the exact machine settings used that day. The British had purchased a commercial Enigma machine from a trade show and studied it extensively. But the military version was different, more complex, with features the commercial model never had. Every attempt to break the military code had ended in mathematical dead ends and exhausted possibilities. The Polish breakthrough changed everything. Hartley spent 2 days reading through documents the Polish cryptographers had included with the machine. Technical papers filled with advanced mathematics, diagrams showing mechanical devices they had built to speed up the code-breaking process, detailed logs of messages they had successfully decrypted over the past 7 years. The Poles had not just broken Enigma through luck or accident. They had developed an entire scientific methodology for attacking mathematical encryption, creating tools and techniques that had never existed before. A mathematician named Marian Rejewski had led the Polish effort. He approached Enigma as a pure mathematics problem, using group theory and permutation analysis to determine the internal wiring of the military rotors without ever seeing inside an actual machine. He derived the mathematical relationships between key presses and lamp illuminations, building equations that described how the rotors transformed each letter. Then he solved those equations, working backward from intercepted messages to figure out possible daily settings. The work required genius-level mathematical insight combined with meticulous attention to detail. Rejewski had both. The Poles had built a machine called the Bomba to automate part of the code-breaking process. 6 Enigma machines connected together, running through possible rotor settings at high speed, checking each configuration against intercepted messages to find settings that produced readable German text. The Bomba could test thousands of settings per hour, eliminating impossible combinations and identifying likely solutions that human cryptographers could then verify. It was the first automated code-breaking machine ever built, a predecessor to modern computers, designed for one specific purpose: defeating Enigma's mathematical complexity through systematic mechanical analysis.
The location offered isolation from German bombing raids, easy rail access to London, and enough space to expand operations as needed. Hartley arrived in January 1940 as one of the first cryptographers assigned to what would become the Government Code and Cipher School. She carried with her the Enigma machine from Poland, the technical documents, and a mandate from Churchill himself to break every German code, read every message, and give British commanders intelligence advantages that could turn the tide of war. The early days at Bletchley Park were chaos. Academics recruited from Cambridge and Oxford worked alongside professional military cryptographers who distrusted the entire academic approach. Engineers built experimental machines based on Polish designs, trying to recreate the Bomba from incomplete documentation. Linguists fluent in German waited for their first decrypted messages, ready to translate and analyze whatever intelligence emerged. And Hartley found herself leading a team tasked with the most urgent priority: breaking the German Navy's 4-rotor Enigma before U-boats cut Britain's supply lines and starved the island into surrender. The 4-rotor naval Enigma represented a quantum leap in complexity. Adding one more rotor multiplied the possible settings by another factor of 26, pushing the total combinations into numbers that human minds struggled to comprehend. The Bomba machines designed for 3 rotors were useless against 4 rotors. Every technique the Poles had developed needed to be recalculated, redesigned, and rebuilt for the more complex machine. And the Germans changed their daily settings every 24 hours at midnight, meaning Bletchley Park would need to break the code fresh each day, every day, to maintain continuous intelligence access. Hartley's team began by analyzing the fundamental design principles that made Enigma so secure. The genius of the machine lay in its simplicity combined with mathematical depth. Any soldier with basic training could operate it. Set 3 rotors to today's starting position, connect 10 pairs of letters on the plug board according to today's settings, type your message, write down the letters that light up, transmit those encrypted letters by radio. The receiving operator, using identical settings, would type in the encrypted message and read the original text from the lamps. No complicated procedures, no chance of encryption errors if both operators used the same settings. But that apparent simplicity concealed mathematical sophistication that most operators never understood. The rotors implemented substitution ciphers that changed with every key press. The plug board added another layer of substitution that remained constant throughout each message. The reflector at the end of the rotor stack sent current back through the rotors along a different path, ensuring that encryption was reciprocal. The same settings that encrypted a message would decrypt it. This reciprocal property was actually a subtle weakness that would prove critical to British code-breaking efforts. The German military believed Enigma was unbreakable because they understood the mathematics of brute force attacks. Checking every possible setting would take longer than the age of the universe, even if thousands of people worked around the clock. Therefore, no enemy could possibly break the code by systematic trial and error. The Germans were right about that. What they failed to understand was that mathematics provided shortcuts. Patterns in their messages revealed information about possible settings. Cribs, known or guessed plaintext, allowed cryptographers to eliminate vast numbers of impossible settings without checking them.
And machines could automate the analysis, testing hypotheses faster than human mathematicians ever could. Hartley recognized that breaking naval Enigma required understanding not just how the machine worked, but how German operators used it. Real humans made mistakes. They took shortcuts. They followed predictable patterns. Radio operators often began weather reports with identical phrases. Submarine commanders structured their messages according to standard military formats. These human behaviors created regularities in what should have been random encrypted text. And those regularities were the cracks through which British cryptographers could break supposedly unbreakable mathematics. The team collected every intercepted German naval message, building a library of encrypted communications. They analyzed message lengths, transmission times, operator behaviors, anything that might provide insight into German procedures. They discovered that U-boat commanders often reported their positions using a grid system. Weather ships transmitted forecasts at scheduled times using standard meteorological terminology. These patterns meant certain German words appeared in predictable positions within messages. If Bletchley Park could guess even a few words of plaintext and their positions, they could use those cribs to narrow down possible Enigma settings dramatically. Building the British bomb machines became the next challenge. The Polish bomba had been elegant but limited in capability. The British version needed to be faster, more powerful, more flexible, capable of testing 4 rotor settings across multiple possible cribs simultaneously. Alan Turing, a young mathematician with radical ideas about mechanical computation, designed a new machine that incorporated logical switches called drums. Each drum represented one rotor position, stepping through all 26 possibilities while checking for mathematical contradictions against the intercepted message. Harold Keane, chief engineer at the British Tabulating Machine Company, transformed Turing's theoretical design into actual hardware. The first production bomb machine stood over 6 feet tall and 8 feet wide, weighing more than a ton. 30 drums rotated in synchronized precision, driven by an electric motor, clicking through possible settings at speeds impossible for human cryptographers to match. When the drums found a setting that produced no mathematical contradictions, they stopped, and operators would test that setting against the full message to see if it produced readable German text. The first successful naval Enigma break came in May 1941, nearly 2 years after Hartley had carried that Polish Enigma across the Romanian border. A German weather ship captured by the British Navy yielded codebooks showing daily settings for an entire month. With known settings, Bletchley Park could decrypt messages, study German encryption procedures, and refine their bomb designs. Those captured documents provided the crucial bootstrap that allowed systematic daily code breaking to begin. Within weeks, British bomb machines were breaking naval Enigma regularly, reading U-boat communications within hours of transmission, giving convoy commanders time to route shipping away from submarine patrol areas. But the captured documents eventually ran out, and the Germans changed their procedures, adding security features that complicated British code breaking. The team had to develop new techniques continuously, adapting to German countermeasures, exploiting new weaknesses as old ones were closed off. It became a mathematical arms race. German engineers made Enigma more complex. British cryptographers developed new methods to break the increased complexity.
And throughout the war, neither side fully understood what the other was doing or how close they were to success or failure. The scale of operations at Bletchley Park expanded beyond anything Hartley had imagined during those early days in Poland. Hundreds of bombs, eventually thousands, running 24 hours a day. Entire buildings full of cryptographers, linguists, intelligence analysts, and support staff. A dedicated teleprinter network connecting Bletchley Park to listening stations across Britain, feeding intercepted messages directly to the codebreakers. And always, relentless pressure to break today's settings before midnight brought tomorrow's new encryption keys that would render all progress obsolete. Hartley moved between different sections, training new recruits, solving stubborn mathematical problems, coordinating between the machine operators and the intelligence analysts. She saw how the British approach differed from the German one in fundamental ways. The Germans had built Enigma for battlefield security, prioritizing portability and ease of use. They assumed mathematical complexity alone provided sufficient protection. The British built their code-breaking operation for industrial efficiency, recognizing that sustained effort over months and years would matter more than individual brilliance or lucky breaks. The mathematical breakthrough that truly changed everything came from an unexpected place. A young woman named Margaret Foster, recruited straight from her mathematics degree at Manchester University, noticed something nobody else had seen. German radio operators, despite strict instructions to use random starting positions for their messages, often chose positions that were easy to remember. 3 identical letters, sequential letters like ABC or DEF, or letters that spelled German words. This human laziness created a statistical anomaly in the encrypted messages that could be detected and exploited. Foster's insight led to a new technique called sillies, named after a particularly lazy German operator whose girlfriend was named Silly. This operator almost always used CIL or LLY as his message starting position. Once Bletchley Park identified his transmission patterns, they could break his messages with minimal bomb time. Then they used his decrypted messages as cribs to help break messages from other operators who shared the same daily settings. One careless operator compromised an entire network, and the Germans never realized their security had been breached through something as simple as a radio operator's predictable behavior. The intelligence flowing from Bletchley Park changed the nature of the entire war. British and American commanders knew where German submarines were operating before they attacked convoys. They understood German battle plans before offensive operations began. They could track Luftwaffe bomber formations and vector RAF fighters to intercept them. Churchill received daily intelligence summaries based on decrypted Enigma messages, giving him insight into Hitler's strategic thinking that no spy network could possibly provide. The Allies were reading the enemy's mail, and the enemy never suspected it. Maintaining security around this intelligence advantage became as important as the code breaking itself. If Germany discovered that Enigma was compromised, they would change their entire encryption system overnight, and Britain would go blind. Every piece of intelligence derived from Enigma had to be carefully disguised.
Convoys couldn't simply avoid U-boat patrol areas without explanation, so reconnaissance aircraft were sent to spot submarines that Bletchley Park had already located through decrypted messages. Bombing raids couldn't target German positions based solely on Enigma intelligence without aerial reconnaissance photos to justify the targeting. The truth had to be hidden beneath layers of plausible alternative explanations. Hartley found herself briefing field commanders on how to use ultra-intelligence, the code name for information derived from Enigma decrypts, without compromising its source. She explained to frustrated generals why they couldn't attack certain targets, even though she could tell them exactly where enemy forces were positioned. The operational security requirements sometimes meant letting opportunities pass, rather than revealing that British intelligence could read German communications in real time. It was a delicate balance between using the advantage and preserving it for future use. The German Navy introduced new complications throughout 1942 and 1943. They added a fourth rotor to their Enigma machines specifically for submarine communications, creating a 9-month blackout period when Bletchley Park couldn't break the new 4-rotor naval code. U-boats operated freely during those months, sinking Allied shipping at catastrophic rates. The Battle of the Atlantic hung in the balance while British cryptographers struggled to develop new bomb configurations that could handle the additional rotor. The pressure was immense because everyone understood that failure meant Britain would be starved into surrender. The breakthrough came through captured materials again. A U-boat forced to surface after depth charge attacks was boarded by British sailors who seized codebooks before the crew could destroy them. Those documents gave Bletchley Park the starting point they needed to break back into the 4-rotor naval Enigma. Within weeks, the intelligence blackout ended. Allied convoy commanders could once again route their ships away from Wolfpack patrol areas. The U-boat casualty rate began climbing as Allied forces, guided by decrypted position reports, targeted submarines with increasing accuracy. Germany lost the Battle of the Atlantic not because British ships or weapons were superior, but because British mathematics was better. Hartley noticed patterns in how different branches of the German military used Enigma. The Luftwaffe was the easiest to break because their operators were often poorly trained and their messages contained predictable content about weather conditions and aircraft readiness. The Wehrmacht was more disciplined, but still followed standard military communication formats that created exploitable patterns. The Navy was the most difficult because submarine commanders understood operational security and their messages contained fewer predictable elements. But even the most careful German operators couldn't completely eliminate the human factors that made codebreaking possible. The engineering required to maintain the bomb fleet became its own massive undertaking. Machines running continuously wore out components that needed constant replacement. Electrical contacts oxidized and failed. Drums went out of alignment, producing false results. The maintenance crews worked around the clock, keeping hundreds of bombs operational because even a single machine breakdown could delay breaking that day's settings by hours. The British Tabulating Machine Company eventually produced over 200 bombs during the war, each one hand-built by skilled engineers who understood they were creating tools that would determine whether Britain survived or fell. Technical innovations continued throughout the war as both sides pushed the boundaries of what was mathematically possible.
The Germans introduced new rotor configurations, changed their key distribution procedures, and added security features designed to frustrate codebreakers they didn't even know existed. Bletchley Park responded with improved bombs, new analytical techniques, and eventually with Colossus, the world's first programmable electronic computer, built to break an even more complex German cipher system called Lorenz. The cryptographic arms race drove technological progress that would reshape computing and communications for decades after the war ended. Hartley saw young mathematicians and engineers developing skills and knowledge that had never existed before. They were inventing new fields of study: information theory, computer science, electronic engineering, automated data processing. The problems posed by Enigma and other German cipher systems forced British scientists to think in entirely new ways about mathematics, machinery, and the relationship between information and physical systems. They were building the intellectual foundations of the digital age while fighting for survival against Nazi Germany. The human cost of code-breaking work rarely appeared in official records. People worked 14-hour shifts in poorly heated buildings, dealing with incredible mental stress and absolute secrecy requirements. They couldn't tell their families what they did. They couldn't discuss their work with colleagues outside their immediate section. They lived with the knowledge that mistakes could cost lives, that German convoys escaped or British ships sank depending on whether they broke that day's settings fast enough to provide actionable intelligence. The psychological pressure broke some people completely. Others thrived on it, finding purpose in work that clearly mattered even if nobody outside Bletchley Park would ever know what they had accomplished. Security protocols meant that most people working at Bletchley Park understood only their specific task without knowing how it fit into the larger operation. Bombay operators didn't know what the machines were actually doing. Translators received decrypted German messages without knowing how they had been decrypted. Intelligence analysts saw finished reports without understanding the cryptographic process that produced them. This compartmentalization protected the operation, but also meant that very few people understood the full scope of what Bletchley Park had achieved. Hartley was one of those few, carrying knowledge that would remain classified for 30 years after the war ended. The intelligence advantage provided by broken Enigma codes arguably shortened World War II by 2 years or more. Historians analyzing post-war records have documented how Enigma intelligence influenced every major campaign. The Battle of Britain was won, partly because the RAF knew when and where Luftwaffe raids were coming. The North Africa campaign turned after British commanders could read Rommel's supply situation and troop dispositions in his own words. The D-Day invasion succeeded, partly because Allied deception convinced Hitler to keep his reserves away from Normandy, a deception that worked because Enigma decrypts confirmed the Germans believed the fake intelligence. Every victory built on advantages that flowed from mathematics and machinery, working together to break supposedly unbreakable codes. German engineers never suspected their encryption system had been systematically compromised throughout the entire war. They conducted security reviews after the war ended and concluded that Enigma had remained secure.
They attributed Allied intelligence successes to spy networks, captured documents, and sophisticated radio direction finding. The mathematical breakthrough that had defeated their cipher system seemed impossible to them even after the war ended. They had calculated the odds and determined that breaking Enigma through cryptalysis couldn't be done. They were wrong because they had underestimated what sustained effort, brilliant mathematics, and industrial-scale machinery could accomplish when all three worked together toward a single goal. The story of what Hartley and thousands of others accomplished at Bletchley Park remained classified until 1974, nearly 30 years after the war ended. When the secret finally became public, historians had to completely rewrite their understanding of how World War II had been won. Battles that seemed like close-run victories were actually fought with massive intelligence advantages. Strategic decisions that appeared brilliant were actually based on reading the enemy's plans in advance. The entire narrative of the war changed once people understood that one side could read the other side's most secret communications throughout the conflict. Hartley retired from government service in 1968, taking with her secrets she couldn't share even with her own family. She had spent 28 years in signals intelligence after the war, applying lessons learned at Bletchley Park to Cold War cryptography challenges. She had mentored generations of younger cryptographers, passing on knowledge and techniques that remained classified even as computer technology advanced far beyond the bomb machines she had helped design. When the Bletchley Park story finally became public, she was one of the few people who could discuss the technical details with any authority. The mathematical principles that made Enigma vulnerable became the foundation for modern cryptography and computer security. Everything we understand today about encryption, code breaking, and information security traces back to work done by people like Hartley during World War II. They proved that mathematical complexity alone doesn't guarantee security. They demonstrated that human factors and operational procedures matter as much as theoretical cipher strength. They showed that sustained, systematic effort could overcome seemingly impossible mathematical challenges. And they built machines that were the direct ancestors of modern computers, creating technology that would eventually touch every aspect of human life. The Enigma machine itself became a symbol of how human ingenuity can overcome any challenge when brilliant minds focus on a critical problem. The Germans built mathematical security into a portable device that any soldier could operate. The Poles developed the mathematical techniques to break it through pure intellectual effort. The British industrialized code breaking, building machines and processes that could break new codes every day for years on end. Each advance built on the previous one, with knowledge flowing across borders and through generations, creating a cascade of innovation driven by the urgent demands of total war. Hartley often reflected on what made the British approach successful when so many others had failed. It wasn't superior individual genius, because German mathematicians were just as brilliant as British ones. It wasn't better resources, because Germany had more industrial capacity than Britain through most of the war. The difference was philosophical. British cryptographers accepted that mathematics alone couldn't solve every problem. They combined mathematical analysis with engineering innovation, statistical techniques, linguistic knowledge, and systematic exploitation of human error. They built organizations that could sustain effort over years rather than expecting immediate breakthroughs. They created processes that turned individual insights into operational advantages that could be repeated reliably day after day. The lessons extended far beyond code breaking. Any complex challenge could be defeated through the same combination of brilliant theory, practical engineering, sustained effort,
and systematic process improvement. The Enigma story proved that impossible problems were often just problems that required the right combination of skills and resources applied consistently over time. It demonstrated that human factors mattered in supposedly purely technical domains. It showed that security was only as strong as its weakest link, and that weakness was usually human rather than mathematical. When Hartley passed away in 1995, her obituary mentioned only that she had worked in signals intelligence during the war. The full scope of her contributions remains known only to the small community of cryptographers and historians who understood what Bletchley Park had achieved. But her legacy lived on in every encrypted communication sent across the internet, in every computer security system protecting sensitive data, in every mathematician studying cryptography at universities around the world. The work she and thousands of others did between 1939 and 1945 created the foundation for the information age, proving that human minds could create mathematics powerful enough to both protect and penetrate secrets on a scale never before imagined. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.